Okay, for lesson 7.5, you can see our learning target is I can solve exponential growth and decay problems. Take a look at this opening sentence here. For many applications, the rate of change of a physical quantity with respect to time is directly proportional to the magnitude of the quantity at that time. And that quantity, some books will even call it a population. It's better to call it a quantity, because you don't have to strictly deal with populations of people and or animals or whatever. But here's what we're really seeing. The rate of change let's even consider for a moment, it was a population. dp dt, they're saying that it's directly proportional. That means there's some fixed constant. Maybe it's a number like 7, or maybe it's a very small number like 0.001. And that number gets multiplied to the population at that time. Now, believe it or not, this is something that is used quite frequently. And because it actually can make a lot of sense. Here's what we're talking about. Let's just say you have a very small group of people. The population, how it's changing with respect to time. If you have a very small population, like a very small city, you generally wouldn't expect to see a huge change in the population. You can see that it would make sense that that change in population is proportional to the population at hand. Whereas if you have a larger population, you might expect to have a larger rate of change. You could get a lot more reproducing and so forth. So that is a reasonable type of a differential equation. And it's actually a differential equation that when you solve, you might be very surprised to see something jump out that you have seen before. Here's what I'm talking about. Let's just say that your population or your quantity is y. Let's also assume, very importantly, that y is positive. At worst, it could equal 0, but we're not even going to have our population equal 0. We'll assume it's always positive. And now we're going to solve this differential equation. We're going to solve this differential equation. Solving will mean that we could actually go about separating variables. That's something that the College Board talks about a lot, and you need to be aware of that phrase, separating the variables. You might think, what on earth does that mean? It means I could multiply both sides by a dt, and I want to get anything with a y off with a dy. I'm going to multiply both sides by 1 over y, or similarly divide both sides by y. What I've just done is I've taken my original differential equation and I have separated the variables. Anything with a y I have gotten on the left side. Anything that didn't have a y I left on the right. You can think, well, for what purpose? Well, ultimately, when you solve a differential equation, guys, you would like to solve for what function of y would this be true? So I'm going to integrate both sides. Now, what's the integral of 1 over y dy? What do you think? Ooh, it's been a few days since we've been here. Antiderivative of 1 over y? Natural log of, now normally you'd say, well, shouldn't I put in the absolute value of y? Well, you could, but I even heard someone just mention that y is positive. We pointed that out earlier, didn't we? So actually the absolute value wouldn't even be needed here. We're going to fix that up in a moment. On the right-hand side, now immediately somebody would say, ooh, put in a plus constant there. We could. I'm going to hold off on just a second. How about taking the antiderivative of c with respect to t? What's that? That'd be ct Now I'm going to put in a constant of plus k over here. I don't want to do a plus c. I already had c used earlier. Now, at first glance, you're going to look at that and you're going to think, well, how come you put a constant on the right-hand side when you took an antiderivative? You didn't take a constant on the left side. You didn't do a plus other variable on the left. Now, granted, you could. But please understand that if you have a plus constant on the left, somewhere over here, and you have a plus constant on the right, couldn't I just combine my constants in the end, like subtract, and just wind up with one constant in the end? That's typically what we do in calculus. When we're solving a differential equation, we'll usually just put one constant off on the right. Well, now what? Well, like I said earlier, our y is actually positive. You can look at it from this way. You could say, all right, so I've got natural log of y equals ct plus k. What do you think I could do to solve for y? What do you think we could do here? Exponentiate. E to the left side, e to the right side. What is e to the natural log of y? Just y. And right here you'd have e to the ct plus k. And wow, that can certainly look rather strange at first glance. You look at that, you think, wow, that looks weird. Well, look, a quick exponent property review. Here's some review, guys. If I gave you x to the a times x to the b, what is that? X to the a plus b. Hey, you know what? You could start from the right side and move to the left. And kids would say, well, why are you doing that? Because then I'd say e to the ct times e to the k. Now maybe, just maybe, this is beginning to look a little bit more familiar to you. You look at this and you think, well, y equals e to the ct times e to the k. Tell you what, I'm going to let t equal 0. You think, why in the world would you do that? Well, I'd get y equals e to the c times 0 times e to the k. What's e to the c times 0, though? Well, it's e to the 0, which is 1. So, in other words, e to the k is your population value at what time? At time equals 0. That means we could say that e to the k is really your beginning population. E to the k is really your beginning population. Put these two things together, and you're going to wind up with this thing. Does that look familiar to you? It's the exponential growth and decay formula. Long ago. Now maybe you learned it with n equals n naught e to the kt. Maybe you learned p equals p sub 0 e to the kt or something like that. But regardless, you would have seen that in Algebra 2. You would have seen that in AMA. And maybe, just maybe, you looked at that and you thought, why in the world is this equation looking the way it does? Now you see why. When you solve that differential equation, when you make the assumption, what we had right here, that the rate of change in the population is directly proportional to the size of the population at that given time, which is a very reasonable assumption, you will solve and arrive right here. So at this point, guys, we're going to revisit this problem. And undoubtedly come up with a problem where when you're looking at this, I think you're going to be a little bit in shock. I think kids are going to look at this and say, now wait just a minute. This is looking a lot like just a pre-calc question, an Algebra 2 question. And it is. Look, if they're telling you that the number of bacteria increases from 5,000 to 15,000 in 10 hours, assuming the rate of increase is proportional to the number of bacteria present, we can find a formula for the number of bacteria at that given time. What I'm telling you is you can immediately jump to this friendly formula. Unbelievable to be here. You look at this and you could say, well, why not is your beginning population? What's your beginning population here, do you think? Oh, 5,000. And you could say, well, your ending population would be 15,000, but that's after 10 hours. Guess what? I can very quickly put all this together and say that when t equals 10, the population was 15,000. Wow, look at that. All I have to do is really, determine a missing piece to this equation. And it's going to be a little bit different from how we solved in the past. I think it's pretty clear kids are going to want to divide by 5,000, which they should. And they'll have e to the 10c here. And it doesn't take much to just cancel this out and see that e to the 10c is equal to 3. Now, guys, in the past, you would actually solve for c. The first time you did these problems, you would have, maybe taken a natural log on both sides and, gotten a solution to what c is. Generally, it looked really ugly. You would store that value for c. Everything would be just fine. What I'm telling you in calc, though, is that so very often we do something very different. We're going to say, hey, instead, let's solve for e to the c. Yes, of course I could find out what c is. But I'd like to do something a little bit different, something easier, something that you can do even without a calculator. What I'm getting at is, wow, on this right-hand side, I just want to have e to the c. How do I get it? What should we do to both sides? Raise both sides to the 1/10. Because powers to powers are more powerful. You'd get e to the c is equal to 3 to the 1/10. Guys, right now you have really all that you need to write your equation. Remember, your equation is this, the y equals y naught. So I'll say y equals, well, my beginning population was 5,000. Now I'm going to have e to the c. E to the c is 3 to the 1/10. It's really like e to the c raised up to the t power. And unbelievably, you are done. You don't have to worry about using a calculator. You now have your exponential growth equation. By the way, more than half of the FRQs on the AP exam are no calculator allowed. Being able to solve like this is definitely helpful. So as we continue on, as we look at part B, they're saying, well, estimate what's happening at 20 hours. Well, plain and simple, you're just going to have to plug in 20 all over 10. Look at that. That just becomes 3 squared. You think about it. And 3 squared is just a 9. You'd get 45,000. That would be your estimate at the end of 20 hours. Finally, for part C, they're saying, when will you be at 50,000? Well, guess what? We just have to finish this thing up real quickly. We're going to let y equal 50,000. And we just have to do a little solving. What do you think we're going to do to both sides?